In the high-stakes world of rocket launches, where planning and execution typically unfold over months or years, Firefly Aerospace achieved a groundbreaking feat last year. With just 24 hours notice from the United States Space Force, Firefly integrated a payload into its Alpha rocket, planned the launch profile, positioned and fueled the rocket on the launch pad, and successfully launched, shattering the previous 21-day record. This remarkable accomplishment was part of Firefly's strategy to carve out a niche in the fiercely competitive space launch market, currently dominated by SpaceX. SpaceX's reusable rockets have driven down launch costs, enabling them to launch more payloads than any other company. However, Firefly's ability to launch on short notice offers a unique and valuable capability that sets them apart. For commercial clients, rapid launch capability is a game-changer. Imagine a satellite ready to generate $1 million in monthly revenue once in orbit. If the next available rideshare launch with SpaceX is 12 months away, that's $12 million in lost revenue, cost far exceeding the launch price for most small to medium-sized satellites. In such cases, waiting for a cheaper launch isn't practical. The opportunity cost is simply too high. Militarily, rapid launches are equally critical. The Space Force's Victus Nox mission, for which Firefly was contracted, underscores this. While the payload's details remain classified, the mission highlights why militaries value rapid response. If an adversary destroys a critical satellite, a swift replacement is essential. If a foreign entity places an unknown satellite or weapon in orbit, a rapid inspection mission is vital. In extreme scenarios, like the outbreak of a major conflict, the ability to deploy assets quickly could be decisive. Firefly has tailored its Alpha rocket to meet these demands, incorporating unique design choices to enable rapid launches. I spoke with Firefly's chief engineer, Jordi Garcia, to understand how they achieved this. From the outset, Firefly designed Alpha for speed, prioritizing quick tank loading and unloading. Garcia explained that their goal was to fuel the rocket in just 30 minutes, a target that required oversized fuel and oxygen lines, quick disconnect systems, and valves. However, larger components add weight, reducing the rocket's payload capacity. This trade-off between speed and performance was a deliberate choice to prioritize responsiveness. Garcia noted that slow fueling over 18 hours would allow lighter components but would defeat the purpose of rapid launches. Additionally, operational constraints, like ensuring technicians don't work more than 12 hours daily, shape their design to allow quick turnarounds after a scrubbed launch, enabling crew rest and a retry the next day. Another key design choice involves propellant temperatures. Unlike SpaceX, which uses supercooled propellants to maximize density and performance, Firefly opts for warmer liquid oxygen at around -290 to -300 degrees Fahrenheit. Supercooled propellants, while efficient, require precise timing as they warm up quickly, limiting launch windows. Firefly's warmer propellants can be topped off as they evaporate, extending launch availability at the cost of some performance. This proved critical during the Victus Nox mission, where Firefly's ability to hold and reset after a scrubbed attempt without draining tanks demonstrated the advantage of their approach. SpaceX's load-and-go method, starting propellant loading 35 minutes before liftoff, leaves little room for delays, as seen when a fishing vessel entering an exclusion zone can force a scrub. This issue became a concern for NASA during SpaceX's Crew Dragon missions, where the load-and-go method raised safety questions after a 2016 Falcon 9 explosion caused by a buckled metallic liner in a composite pressure vessel. Firefly's design mitigates such risks, offering greater flexibility. Firefly's proximity of engineering, manufacturing, and testing facilities near Austin, Texas is another critical advantage. Unlike SpaceX, which tests engines in McGregor, Texas, while engineering Falcon 9 in California, or Blue Origin, which tests at NASA's Marshall Space Flight Center in Alabama while engineering in Seattle, Firefly's integrated setup accelerates development. Engineers can iterate quickly, test components on site, and address issues in real time. This was evident in their engine development, particularly the Reaver engine's tap-off cycle, a first for orbital rockets. Unlike SpaceX's Merlin engine, which uses a gas generator cycle with a separate combustor, Firefly's tap-off cycle siphons hot gas directly from the combustion chamber to drive the turbopump. This eliminates a complex component, reducing weight and increasing reliability, though it introduces challenges like managing high temperatures and potential soot buildup from the hydrocarbon fuel, RP1. Firefly has developed proprietary solutions to mitigate these issues, though details remain confidential. The Reaver engine's pintle injector further enhances simplicity. Unlike the Saturn V's F1 engine, with its complex injector plate prone to combustion instabilities, the pintle injector uses a single, robust design that creates recirculation zones in the combustion chamber. These zones improve fuel efficiency and provide a cooler region from which Firefly taps gas for the turbopump, avoiding damage to turbine blades. This ingenious design reduces complexity, cost, and potential failure points, aligning with Firefly's goal of reliability and responsiveness. Firefly's composite manufacturing also sets them apart. Their Alpha rocket features the world's largest all-composite liquid oxygen tank, a linerless design that eliminates the metallic liner implicated in SpaceX's 2016 explosion. Linerless tanks are 20% lighter but challenging for cryogenic applications due to moisture-induced cracking at -300 degrees Fahrenheit. Garcia described the painstaking process of perfecting this tank, involving precise control of moisture and humidity during manufacturing, followed by rigorous testing with liquid nitrogen and structural loads. Each tank is tested at 10% above expected flight conditions to ensure reliability, a process refined through years of trial and error. Thermal protection is another area where Firefly balances simplicity and performance. They use natural cork as a lightweight, cost-effective insulator to shield composite tanks from aerodynamic heating. While effective, applying cork is time-consuming, and Garcia dreams of a naked rocket without it, though this remains a future goal. Firefly's automated filament winding machine further streamlines tank production, laying continuous carbon fiber for stronger, lighter tanks compared to manual layups. This automation is crucial for scaling production to meet demand for rapid launches. Supply chain and vertical integration are also key. Firefly focuses on in-house development of critical components like engines and structures, reducing reliance on vendors who may not prioritize small orders. Garcia recounted a Victus Nox incident where a commercial off-the-shelf component failed, and the vendor offered little support. Firefly's team redesigned and qualified a replacement in just 41 days, leveraging their in-house capabilities and young, dedicated engineers. This agility underscores the advantage of controlling their own destiny. The Victus Nox mission itself was a logistical triumph. Firefly received the target orbit with 24 hours notice, requiring rapid trajectory planning, ground simulations, and payload integration. They pre-ran simulations for likely orbits, allowing quick adjustments when the call came. Bureaucratic hurdles like FAA paperwork and exclusion zone coordination were navigated with Space Force and FAA cooperation. Payload integration was streamlined with custom ground support equipment, enabling rapid encapsulation in a clean environment with precise humidity control. Even mating the payload to the rocket was optimized, with chamfered bolts and timed procedures to shave minutes off the process, drawing parallels to an F1 pit crew's precision. Firefly's achievements extend beyond Victus Nox. They've since launched successfully again with the Noise of Summer mission and are preparing for a lunar landing with their Blue Ghost lander. To compete with industry giants, Firefly is developing a medium-lift rocket with Northrop Grumman, capable of carrying 16,300 kilograms to low Earth orbit, using the same tap-off cycle for its Miranda engines. The first flight is planned for 2025. Firefly's success hinges on its talented engineering team, led by figures like Garcia and VP of Engineering Bridget Oakes, whose expertise and proximity-driven workflow enable rapid innovation. For those inspired by Firefly's story, their job board lists openings from HR to launch engineering, all based near Austin. The space industry is fiercely competitive, but Firefly's focus on responsiveness, simplicity, and in-house innovation positions them as a strong contender. Their ability to break records and solve complex problems in real time demonstrates a promising future in a market where speed and reliability are paramount.